Hey guys, welcome to the second episode of Vector Analysis for Physics students. In the last episode, we talked about inner product and outer product and differentiation for vectors. So it's kind of like the basic concepts in vector analysis. It's just the basic operations between two vectors. Today we're gonna move on to three more important and more commonly used concepts: gradient, divergence, and curl. They all have their own related theorems, and we're going to talk about that in this episode as well. Okay, before we actually move on to the actual content, please allow me to introduce some of the notations that we will use in this video. Okay, first of all, gradient, divergence, and curl, they all involve the use of the nabla operator, which looks like an upside down delta. It's called del or nabla operator. So all we need to know about this operator is that we can just think of it as a common vector. Nothing different, nothing different with other vectors, except that it just has operator property. It has three components, obviously, in the x y z axes. So it has a derivative operator. It takes a derivative on the perspective axis. It's just nothing different from any other vectors except for its operator property. Okay, that's our first notation, del operator. Okay, our second notation is that df. df is actually represents area element. However, it's a vector, so its direction is normal to the surface of the area, like I drew here. So it takes the modulus of this vector is just the area of this infinite small rectangle. So it's the modulus is its area, and its direction points as its direction is normal to the surface of the area. Okay, next is like this. So it's like a partial sign before v, and v is volume. So the partial sign of v means it's the boundary of the volume, which is equivalent to surface areas. So for example, we have a block here. Oops. So we have a block here. So it's a volume, obviously. So the boundary of the volume would just be all six surfaces, like the shaded region. So the boundary of this cube is just its six surfaces, and we denote all these boundaries by adding a partial sign in front of it. Actually, sign comes from topology. In topology, an object, the boundary of an object is described using the partial sign. Okay, then ax means the vector A is component in the x direction, so it's kind of common in a lot of literature. And next, in all my calculations below, phi means a scalar field. Sorry, phi means a scalar field, and the A with the arrow on the top of it means some vector field. So how do you understand a scalar field or a vector field? So for example, a scalar field can be a temperature field. So imagine suppose we have a space, and for every point in space we have a function t x, y, z. So T stands for temperature, for example, in this case. So for every point, and we have a scalar value that is dependent on its coordinates, in a system. In this case, it's a Cartesian coordinate system. Okay, for the vector field, that's another like opposite thing. So like for example, the velocity field, x, y, z. So in a system, so every point in the system has a vector value, and this value does only has like, for example, we have a space of two-dimensional space over here. So for every point, it has a direction, and like its coordinates is x, y. So every point has a vector value on this point. So that's a vector field. It's pretty easy to understand. Okay, now we move on to our first concept, gradient. So what a gradient does is that it turns a scalar value to a vector value by putting a nabla operator in front of it. For example, we have a scalar field over here. So it's phi, so we put del in front of it. We can just, like I said, we can just view the del operator as a common vector. So like phi is like a phi is like some kind of scalar. So scalar times a vector will yield a vector. So, and that's how we understand it. The operator turns the value from scalar to a vector. And since it's an operator, we just put this phi after all these derivatives. Like I said, we can just it's kind of simple to understand. We just take the derivative of phi in direction of the x-axis and times the unit vector, unit direction vector ex. Oh, I forgot to mention one more convention is that ex, ey, ez. They are unit vectors in respective directions x, y, z. We'll use the Cartesian coordinate system for simplicity in this video. Okay, so that's like the definition of the gradient of a scalar field. Now we are going to move on to the relevant property of the concept of the gradient concept. So all the properties I'm going to include in this video has a common feature. So it can lower the dimension of the integration area. For example, in this property here, initially we're integrating over the total volume of the field. That's like a three-dimensional thing. And on the right side, we successfully converted a three-dimensional integration area to a two-dimensional integration area because it's the boundary of the volume. So it's just the surface area of it, just as we talked about. So that is one of the function of the properties. It lowers the dimension. So another thing is that most of the properties I'm going to talk about today can eliminate the del operator. It's kind of like the del operator adds the difficulty of the calculation. So after we drop it, the calculation will be much more simpler. Like it's just direct, like on the right side here, it's just direct cross dot product between two vectors. So that's why these all properties exist, and they're kind of useful as far as I'm concerned. So the first property I'm going to introduce here is this, and its proof goes as follows. So we just consider the x component because the del operator here on the left hand side, and the right hand side, they are all just like, if the x component is equal, then all the components were equal, just as we flipped all the x signs in here and turn it to y and z. So it's kind of like cyclic. So we just need to prove the x component of the two expressions are equivalent, and that's all we need to do. Okay, so all the proof here just essentially it's made a substitution. So on the right on here we have a bunch of stuff over dx. So we replace dx into replace it into dx dy dz, 1 over dx dy dz times dy dz. So it's kind of returned like this. So why it helps? Because it is if we use its geometric significance, we can turn it into this. Since dy dz is like the dy segment on the y-axis times the dz segment on the z-axis, it's just like an infinite small area element. And the first part, the first denominator here is just like an infinite small volume. So after make this substitution, we can successfully prove the whole property using the concepts in calculus. Okay, now let's delve into what it actually means to take the gradient of a scalar field, del phi. What it actually means, like from a geometric or intuition perspective. Let's first consider this: del phi, the gradient of a scalar field, times the unit vector along the x-axis ex. The result is simply a partial phi over the x-axis, right? Because ex is perpendicular to both ey and ez, so it just results in this. So this expression means the rate of change on the x direction, right? So similarly, we can derive the same thing for the other two axes. So then we can derive that del phi times a random unit vector u in a space is the rate of change of the scalar field phi on the direction of u. So that's kind of like a obvious thing, right? So with this being proven, we can now consider the maximum value for this expression, del phi times u. What is maximum? Since u is just a unit vector, its modulus is 1, and is a dot product, meaning that its maximum will be simply del phi, the modulus del phi times 1, which is just itself. So what it actually means that when the unit vector u points at the same direction at the del as the gradient of the scalar field, its dot product will be maximized, and its value will be just the gradient of the scalar field just itself, the modulus itself. So what it actually means that is that the gradient field, the gradient of a scalar field is its direction. Its direction is points as the rate of change, the direction on which the rate of change of the scalar field is maximum. Okay, let me write this because I was a little bit ambiguous about what I said. Let me write this down. The direction of del phi points to the direction where the scalar field phi changes the fastest, which means there's a faster rate of change along that direction, because the del phi times the random unit vector, only when the unit vector points in the same direction as del phi, that's their dot product will reach its maximum, which is del phi itself. So we have proven that. Okay, so that's like the geometric meaning of the gradient function, the gradient operator. Okay, now let's move on to divergence. Divergence, it's like the cross dot product between the del operator and a vector field A. So the dot product between two vectors will be a scalar. So obviously here, as I just said, we can just view the del operator as a common vector. So the dot product will be just a scalar. So we obtain this expression. So it turns the divergence turns a vector field to a scalar field. I put it down right here. So now let's consider what this expression means for what it actually means to take the divergence of a vector field. So let's consider a vector here like A, and we're considering two dimensions here because for simplicity, like here's the y-axis and here's the x-axis. Okay, so we can we divide into two components, and this is ay, this is ax, and if we consider the meaning of partial of ax over the x-axis, we're just calculating the rate of change of the x component on the x-axis. So if this term is positive, if it's positive, it will means that there on this specific point there is component on the x-axis pointing out. If it's negative, so it means if it's positive, means like there is vector pointing out. If it's negative, it will be like the arrow will be pointing backwards. It's similar for the x-axis. It's like if the power of ay over the y-axis is positive, it means that it will on this point P here, there will be a vector pointing upward. If it's negative, meaning that's the vector generated by this point will be pointing downward. So it's like a quantity that measures the source, the source of on the point. So if the value is positive, meaning that there will be vectors coming out of it. If it is negative, it's just like there's vector flowing into it. So if it's positive, means like vectors out. It's negative, means flow into. So it's like a quantity that can determine whether the point is a source or not, and that's how we view it geometrically. Okay, now we move on to its property. It's very important. It's called Gauss theorem, and it's very useful in electromagnetics. Like similar to the last one, it also lowers the dimension of the integration part part lowers from 3-dimensional to 2-dimensional things. Just like this part is the surface area and this part is the volume. So to prove it, we make the same substitution. We substitute 1 over dx into 1 over dv times the area element, dy times dz. Okay, and then we can successfully prove it using the same calculus concept. So it's very similar to our last proof. So basically, it's just like a change of the sum of the quantities inside. So that's how we prove it, and this is Gauss theorem, and it's very useful in electromagnetics, as I just said. Okay, now we move on to one of the most complex parts in this video. It's called the curl. It's kind of hard to visualize what exactly is a curl, because it turns a vector field into another vector field. So this part, after you have done like here is scalar multiplication of the del operator, and here is the dot product of the del operator, and now we come to the cross product. The del operator cross product the vector field A. Remember how we can calculate the dot product? We can algebraically we can use the determinant, as I said in our last episode. We can use the determinant, and the first row will be just the unit vectors on x, y, z, and the rest two rows will be its components along these two axes. So like we treat the del operator as any other common vector, and we obtain this determinant, and calculating it will help us obtain this expression. Okay, so what it actually means. So we from the form of this expression, we can't actually derive anything, because it's pretty messed up. But actually in physics, if we just use some tools to visualize it, we can know that represents a circular density of the field. Here's an example of a uniform circulation, a vector field with a uniform circulation, curl, with the uniform curl. So every point on this field, its curl will be constant. Why? Because there will only be one vortex on the center. It's the center of the vortex, and all these arrows around it will just rotating around it on the same rate. Like it's not an arrow is breaking its order, so it's all rotating at the same rate. So, and that's why the curl of this whole vector field, it will be constant. And that's how we understand it. It's just a circulation density. Okay, now let's look at the Stokes theorem, which is the theorem related to the concept of a curl. It takes a form like this. So we turn an integration over an area into integration into an integration just over the boundary of an area, which are its edges and its sides. Okay, so the proof, similarly, we just prove for the x component, because the expression are still cyclic. So for the left hand side, we just put down what we had on the expression of del times vector A on the x axis. So we just put down and what we have, and times the surface element on the x direction, which is dy times dz, because x is flowing like in this direction, and this is y, this is z. So the surface element will be obviously like this, and be dy times dz. Okay, so what we're trying to prove is that this expression will be equivalent to the x component of this expression. So okay, on the right hand side, we just have which we essentially want to calculate is just the vector A times it's like this flows over all the edges of the surface. And because we're taking infinite small area, so its edges will be infinite small as well. It's so what infinite small means is that this edge is so small, it's so little, so that the value on the function for the vector function on this side will be constant. So this side will have just a constant value. Like I denote it as ay bracket 1. So this is the first side. This is the first side. This is the second side. This is the third side. This is the fourth side. So why do we integrate over the boundary of the area in such a sequence? So we're doing it like doing it counterclockwise. Why is that? So it's like a convention we're following. It's can be how the a sequence we're integrating can be determined using a right-hand rule. Like for example, here I drew a diagram here. So if you point your thumb over the same direction as DF, the surface element, if you like point up your thumb like this, the rest of the four fingers will form a curl, and the direction of the curl will just indicate the direction of integration we're following, and it's counterclockwise. If you do it the other way, like if you're doing it clockwise and you forgo this, you just you disobeying this rule, what we will find is that your result will be will have a negative sign in front of the second of the second on the right hand side because you're integrating it backwards. It doesn't really make a difference, but it's just a convention we're following to make this looks better. Anyway, so okay, we're integrating it, and we're assuming that the on the edge of this triangle, all the value is the same. So it's just like one value times the dy, because we're considering an infinite small rectangle, and we'll just like derive this equation. And since you're going from like for the third and fourth edge, because you're going this way, which is like the counter direction of the y-axis. The y-axis is going this way. So you need to add a minus sign in front of the dy and minus sign in front of the dz. Okay, and now we pick up the like terms, and we just take the dy and dz out, and we need to calculate the thing inside this bracket. So it can be simplified to this. Why is that? Because let me draw this. Okay, so this is ay bracket 3, and this is ay bracket 1, and this is y axis, and this is z axis. So we need to calculate the difference between this. So what we can write is we can just violently just break down ay3 into ay1 first, and then we take the derivative of ay over the z-axis, and we times it by another dz. We can write ay3 as this. Okay, and we substitute this back in our equation here, and here we have a minus sign, but here we don't, because ay3 is the positive direction in z-axis as ay1, and however ay2 is on this side, and ay4 is on this side, because so ay2 equals to ay4 plus something. Okay, and so this will be positive and this will be negative, and we substitute all this back in, and we will obtain the left hand side, this part of the expression. So, and this is solved, and that's how we prove the Stokes theorem. And that's all for the three concepts we talked about today. Okay, then let's see some of its applications in electromagnetics, and let me show you guys how useful are these properties. First of all, we can prove that the gradient of any scalar field is curl-free. Why is that? Okay, now let's see. First, if we want to integrate the gradient of the scalar field along the edges of the boundaries of an area, we can find that it's zero, because given its definition, this expression will yield a phi on the, like if we integrate, like if we have a like a scalar field over like this. So, and this is R1, this is R2. This integration will just simply obtain the scalar value on R2 minus the scalar value on R1, because given the definition of the gradient, it's like a derivative, and by integrating it, we'll just turn it backwards. Okay, so if for a closed loop, R1 and R2 will just overlap, so the value will be just zero. So this integration will be zero for a closed loop, and using Stokes theorem, we can turn it backwards, like increase the dimension from a one-dimensional thing to a two-dimensional thing, and over a surface, over an area, we can obtain this stuff inside, and since this expression is equal to 0, we can just simply derive that the integrand inside it is 0 as well. If we were to say it in like fancy words, the gradient of any scalar field is curl free, meaning as the curl is 0. So there's no vortex or any rotation inside any scalar field. Okay, now let's consider the same thing for a vector field. Okay, first need to introduce a concept called closed surface. It's actually come from terminology in topology. So and these two the first side is the sphere, and this one it looks like a donut. It's actually called a torus, and it's a very typical example in topology because as often used as example to explain what was called homotopy equivalence. Yeah, that's what it's called. Okay, so like we in topology we often say that a donut is the same thing as a coffee as a cup or like a coffee mug. So basically, you have the same thing, and under certain transformations, they can one can transform into another. So anyway, it's tangent. It's tangent. So these two objects are called they are both called closed surface. Why is that? Because its boundary is smooth. There are no any edges on the surface, so everything's smooth. However, it's considered a cylinder. A cylinder has the edge of it's sharp. So like if you touch your hand on this edge, like this is there will be a right angle. Like if you look at it like in front of it, it'll be right triangle. So it's sharp. It's not smooth. It has an edge. So we call this kind of thing called it has an open surface. It's the surface of the cylinder's open surface. So for a closed surface, the boundary will be 0. So this, strictly speaking, it's like it's an open set in topology. So since we're integrating over an open set, the result would be naturally 0. And if you use Stokes theorem to make it backwards, you'll get an expression for integration over an area, and you use Gauss theorem another time, you can turn an integration over an area into a volume, and you can inside the integrand we have this expression, and since the expression is 0, the integrand is 0, so the curl of any vector field is divergence free, meaning that its divergence is 0 everywhere. And these two are two important properties of respectively scalar field and vector field, and that's how the two properties I just introduced to you can be applied into electromagnetics, and yeah, that's how useful it is. Okay, that's so much. So far we have covered all the content for vector analysis for physics students, and I hope you guys can find it inspiring or beneficial to studies. And thank you guys for watching.